Yeah, just 1 second before I respond. I have to do something with my pointer here so that it remains visible. Yeah, thank you very much for the kind introduction, Felix. It's a pleasure to be in Berlin again. Yeah, I would love to be there in person, of course, but maybe we can do that at a later point in time. Yeah, you're right. So synthesis was maybe my synthesis and intonation, my earlier work. It has never gone away, and we will encounter a bit of synthesis in this talk as well. I trust you can hear me fine, probably see me, but that's less important, I guess.
Audio quality is super,
yeah.
very good. Yeah.
Okay. And yeah, so about so I probably won't be able to watch the participant list or any virtually raised hands or so as I go along with full screen mode. So if there's anything urgent, if you have urgent questions that you would like to ask during the presentation, please feel free to do so. And maybe Felix or somebody else can just pay attention whether there is anything. Or you just, like our dean recently said, you just shout in, right? That's another possibility. Okay, yeah, I was aiming for something like 40 minutes. We'll see how it goes. And I will be available after the talk for as long as you guys are interested. So this is about a phenomenon known as phonetic convergence, which has been demonstrated in both human-human and in human-computer interaction. And phonetic convergence is usually defined as an increase in segmental and supersegmental similarity between two interlocutors. And that happens fairly rapidly and dynamically as the conversation unfolds. It can be subsumed under a term known as vocal accommodation. So accommodation also means that interlocutors sort of negotiate a little bit their communicative behavior in the conversation. And for us as phoneticians, we are specifically interested in the verbal or the vocal communication. I'm reporting on results from a still ongoing project funded by the German Research Council at my lab. The title is Phonetic Convergence in Human-Computer Interaction, and I'm reporting work that has been done almost 100% by these two guys, with some input from me, of course, and Ingmar Steiner as well. Iona Gessinger and Eran Rave are PhD students in the project. Actually, Eran defended on last Friday his PhD thesis, and he joined a private company since, so he's not with us any longer. Iona Gessinger will submit her PhD thesis in, I would say, 4 weeks or so from now. And Ingmar Steiner was a PI, co-PI with me from the beginning, but he left the university 2 years ago and joined the same outfit that Felix is also affiliated with.
Audiring.
Audiring, exactly. So he's not formally a PI anymore, but he's still involved a little bit. Yeah, vocal accommodation has been studied a lot, and especially in human-human interaction, but much less so in human-computer interaction. And there have been a number of explanations that have been put forward to explain what's going on here, why interlocutors would actually become more similar to each other as they go along. Famously, there are two main theoretical frameworks behind the attempts to explain this phenomenon. One is known as CAT, Communication Accommodation Theory, proposed by Giles and Shepard and colleagues. You can see that the early date here from now 30 years ago already, but still ongoing theoretical framework here, developing one. And it's emphasizing the social motivation, right? So we become more similar to each other in our speech patterns in order to reduce the social distance between us. So that's the gist of it. An alternative approach, not entirely contradicting, more or less complementary, is the interactive alignment model by Martin Pickering and Garrett. We just had 2 weeks ago a presentation in our colloquium by Pickering in Saarbrücken. And this is an approach that emphasizes the kind of monitoring that the interlocutors perform, monitoring of the interlocutor's behavior, of their own behavior, and they're constantly updating the state of the dialogue and the representation of the dialogue on all kinds of levels, right? So for linguists and phoneticians, we would say particularly interested in something like various linguistic levels, semantic, lexical, but all the way down to the phonetic level, although Pickering always emphasizes that he has very little to say about the phonological and phonetic level. He has mostly worked on syntax and lexicon and semantics. And recently, the Stuttgart group from the IMS, especially Nathalie Lewandowski, Antje Schweitzer, and Matthias Hilka, have emphasized the amount of individual variation that is going on in this kind of phenomenon, and the differences in individual dispositions of the interlocutor. So there's apparently some people, as we will always also see in the results that I'm going to present, individuals who are very, very prone to accommodating very fast, right? And others are, yeah, so-so, right? And there's also always a group of experimental subjects who maintain their patterns, right? The reasons for that may be manifold, and Lewandowski and Ilka have a nice paper that discusses various traits, individual traits, personality traits that may or may not favor accommodating behavior. In human-computer interaction, the body of literature and research is much smaller. There has been some early work by Nass and Brannigan. Here, Nass, you can see it's a pretty old reference already. This has given rise to what is now known as the CASA framework, computers as social actors. And that builds on the observation that humans tend to treat virtual assistants, virtual tutors, or those kinds of things as agents with which you interact in a social way. And that is also what we find, as we will see as we go along today. We will see that the behavior of our experimental subjects doesn't really change whether they are interacting with a human or with the computer. And an interesting paradigm that we've also used in our project is known as the Wizard of Oz experimental paradigm. This is basically experimental subjects are led to believe that they are interacting with an autonomous system, with an autonomous computer and dialogue system, right? Whereas in reality, there is a wizard, a person behind the scene, right, in the control room next door or something, controlling all or a subset of the behavior of the dialogue system, right? But it's set up such that the experimental subject thinks they're indeed interacting with a computer that's autonomous in its behavior. And it actually works. So in post experimental interviews, we always ask the people, so and indeed basically nobody ever suspects that they are led along, basically. So here's the outline of my talk. So I will first talk about our shadowing experiments, and I will explain what that means. Then the experiments using the Wizard of Oz design, and then talk a little bit about artificial interlocutors and a prototype system or a proof of concept system of an adaptive spoken dialogue system that can adapt or accommodate to human interlocutors. So in the shadowing experiments, we used a number of native speakers of German. There were always, all the sentences involved were pretty short, mostly out of the blue. We were focusing in this first set of experiments on segmental contrasts, on which we assumed experimental subjects would accommodate, and that has not been done before. Most of the work has been done on rather global prosodic properties like overall speaking rate or overall loudness, pitch range and variability and these kinds of things, but not this fine phonetic detail. So the first segmental contrast that we investigated, actually we did both of them in the same experiment. The first contrast was between ich and ich at the ends of words. So ich embodying, for instance, so spelled as ig, right? Embodying a suffix, but not necessarily a suffix of adjectives. Could also be in words like König, king, right? And both variants, ich and ich, are pretty widespread in Germany, right? So I guess all of us have been exposed to both variants. The ich variant is the standard German variant, but ich is also widely used. And there are all kinds of misconceptions about what is the standard variant, what has higher prestige. Also, we found out from our experiments, from our experimental subjects, that they had all kinds. So they used ich, right? And they said, but I know I should use ich because that's the standard, right? But of course it's not. Anyway, so either variant is not unusual and not very surprising if you encounter that in the dialogue. And the second contrast is in the vocalic system, the contrast between long e and in words like Käse. So for me, where I come from in Rhineland, right, we speak proper German. So we make a distinction between Ehre and Ehre, Beeren and Bären, etc. So for us, it's clear it's Käse, right? In the north, I guess, a merger is happening or has happened. It's mostly merged into E, and in the south, especially in Baden-Württemberg, to A, right? But again, we are all sort of aware of this, right? We don't find it unusual if somebody says Käse. Okay, and the procedure is, there's a baseline study, a baseline condition, a baseline task, in which the experimental subjects are asked to produce sentences that they are exposed to in written form, like, for instance, die Bestätigung ist für Tanja. Then, after the baseline recordings, we give them a little bit of a game to play for 10 minutes or so, so they get the linguistic task. And then afterwards, they are exposed to stimuli, most of which contain either the ich things or the ER things, right? And there are three types of stimuli: naturally produced stimuli by a model speaker, diphone synthesized versions, and HMM synthesized versions. One individual experimental subject is only exposed to one type of these stimuli. So they never hear the same sentence with different voices, basically, right? So there's no learning involved there. And then we have a post-exposure recording, again, with sentences that contain these phenomena, and then we check whether they changed. So first of all, in the dialogue, whether they changed their behavior and how lasting that is. So this is the general setup, and I'll just play you natural recordings from our experimental subjects for these contrasts. So here's an example of the staubig.
Staubig.
Can you hear that?
Yeah.
Okay.
Yeah.
So this should have been ich, right?
Bestätigung.
Oh, this is now sorry, I clicked the wrong one. So, staubig.
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 So the last two produced staubig. Okay. So this was their natural way of producing it. They didn't know about this, right? They didn't know what we were interested in. They just read these sentences and produced them in the most natural way. So the same for the ER contrast.
Bestätigung.
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 Right. So we had not exactly equal, but by and large, even distributions of people who said E and others that said E, and the same for the Ich contrast. So then they were exposed to, as I said, female and male stimuli in the natural and the two different diphone synthesis versions. And we made sure that they were always exposed to exactly the opposite of what they did. Right? So when a subject who would always say staubig would be exposed only to versions with ich and the other way around. Right? So that was one reason why. Another reason why we had this little game in between, not only to make them forget about what they said, but also to be able to set up the opposite set of stimuli that they would be exposed to. And then they were exposed, as I said, to the opposite in three ways. If only we could click correctly. So.
Die Bestätigung ist für Tanja.
And then that was natural, diphone.
Die Bestätigung ist für Tanja. Die Bestätigung ist für Tanja.
So this was all with a for a subject who would naturally produce e. Okay. Sorry. Okay. So we now have the natural, diphone, and HMM condition. And then we can see that for instance, in the natural condition, 90% were indeed exposed to the opposite, but 10% to the same version that they produced. How that? It is because we gave them a number of such items to read in the baseline production, and some participants are not consistent. So sometimes they say Käse and sometimes they say Käse. Most of them were very consistent, but some were not, so that you always get this residual of a few people who would happen to say the same thing as the role model. And that's the same for the three conditions of stimuli. And then in the shadowing phase, so what's shadowing is actually? Shadowing is speaking the same sentence after they heard the role model, right? The role model stimulus. In the instruction, we made very sure that we didn't instruct them to imitate or speak exactly as or something like that, right? It was just made explicitly clear that they were expected to say the same sentence after they heard the other one. Right? So for the natural stimuli that they were exposed to, all of a sudden, only 60% stayed with the version they had, and the others switched. And in the post-test, when they read sentences again, they went back a bit, right? But not all the way. And this pattern repeats for all three different types of stimuli. Not exactly quantitatively, but qualitatively, it's the same pattern. All of that is statistically significant, except the difference between the baseline and the post-production when subjects were exposed to HMM synthesis. We can speculate why that is, but maybe that would be too detailed now. So interim summary, Ich and Ich worked nicely for the natural and diphone synthesis, natural voice, diphone synthesis voice. For HMM, there was a tendency in the right direction, but it was statistically not significant. So for A and A, it's better to look at something like the vowel space. So if this here is the black ellipses, and the little orange thingy here is the center of the ellipses, is the role model right? Then a typical experimental subject who would, in the baseline condition, produce the green stimulus in this F1, F2 form and space, would then, in the shadowing task, all the way move to an area indicated by the reddish ellipses. So going clearly in the direction of the target. And in the post production task would go roughly halfway back. So this worked nicely for the natural stimuli. It for HMM was the same as with the consonant contrast, but for some reason the diphone role model did not trigger this kind of behavior in a significant way. Again, we have some ideas about why that happened. It has to do something with the diphone synthesizer and the diphone inventory available, but maybe that's, you know, too much post explanation and trying to explain something away. So this is how the shadowing experiments worked. And now let's look at the Wizard of Oz experiments. The setup was a little bit different and maybe slightly more complicated. So this, we told the experimental subjects that they would interact with an autonomous system, a system that was our attempt of building a computer-assisted language learning tutor with German as a foreign language. And the task of the experimental subjects, so we told them, was to evaluate that system, to interact with the system, and then give us some feedback. Right? So they had no idea that they were actually tested for accommodation. The system is called Mirabella, so this name will come up all the time. In reality, the person, the wizard behind the system was Iona herself. She was the wizard. Again, we had natural speech stimuli available and one version only of the synthesized utterances using the HMM system. We excluded the diphone synthesizer because it could not trigger the vocalic contrast accommodation in the shadowing experiment. The subjects had to solve two tasks jointly with Mirabella, testing again the same kinds of segmental contrasts that we talked about, and in addition, an intonation contrast between rising and falling constituent questions. I'll explain what these are. We had 20 native German speakers, and our expectation based on the human-human interactions before was that some users would converge to Mirabella, some others might maintain their preference. We shall see. So baseline. In the baseline, there were two tasks, again, producing the sentences, with some of which contained our interesting contrasts, and also question intonation by doing something like this here. They're shown an image, an object, and then they had to say something like das Wort, whatever that represents. So I guess Käse, kenne ich, or else they don't know it, but that never happened. Right? And in the question intonation, they were asked to ask questions to Mirabella. Right? And they had some frames here, some fragments of utterances that they were supposed to use, always with WH pronouns starting the sentence. And that's what's known as WH questions or constituent questions. In testing, the same tasks, and I'll lead you through this. So let me jump ahead and I'll explain how this works. So in baseline, I already explained. In the testing phase for the segmental contrasts, we gave them a map task. They had to solve the map guidance jointly with Mirabella. So they actually were the instruction givers, and Mirabella was supposed to be the instruction follower. And they moved through the map and named the objects that they encountered along the way, some of which contained the segments of interest. Right? And sometimes they encountered something like a question mark. They didn't know what the object behind that was, so they had to ask Mirabella about that object. Right? That gave Mirabella a chance to name these objects again with the interesting segmental units.
Das Wort Käse kenne ich.
So this guy would say "ä," and then Mirabella would always produce "e" stimuli, just as in the shadowing task.
Das Wort traurig kenne ich.
So this guy said traurig, so you will always be exposed to König instead. Right, and so I explained this task as well. So what are the results for segmental pronunciation? Right. We had in the baseline about 45% of people who used the preference, had a preference of ich consistently. The same number of people had a preference of ich, so this was nicely balanced, but it was roughly a coincidence. And there were a few who were inconsistent. And in the map task, when they were exposed to the opposite thing, they changed a bit, right? So those who had a preference for ich, only 31, this number went down to 31%, right? The same for the preference of ich. They switched to the other alternative, the one that they were exposed to. And consequentially, the numbers of the same went up. So this was for the natural stimuli, and it's just repeated for convenience here on the left panel. In the synthetic stimulus condition, it's roughly the same. The numbers are slightly different, right? But overall, it's the same pattern again. And for the EE, we again try to illustrate that by means of a vowel space in two-formant plane. Blue is the Mirabella target, and the baseline is green. And during the map task, they used this region here, which is closer to the target. Right? So for question intonation, then there was a task where there were animals, various animals that were hiding behind a house, and the experimental subjects would have to ask Mirabella where a given animal was hiding. So it's a WH question, and in German there are two versions, two intonation versions for these. I'd say the default version is an intonation contour that is basically the same as, or very similar to that of a declarative, of a statement, right? So something like,
Wo hat sich der Löwe versteckt? Wo hat sich der Löwe versteckt?
So the second version was this one where the intonation contour is rising at the end. That's also a possibility. The default is the falling one. The rising one is usually has a bit of connotation, like the speaker is either polite or a bit uncertain or is verifying something, right? But the default out of the blue intonation for a WH question is the first one here. Wo hat sich der Löwe versteckt? Wie viel Uhr ist es? So all the functional load of marking the sentence mode as a question is already on the WH pronoun, right? So there's no need for intonation to also mark the question type, but you can if you wish. So in the first round, subjects were always exposed to falling, and in the second round, always exposed to the rising variant. So in round one, the number of rising, the number of falling contours had increased after the subjects were exposed to falling contours, right? And after the second round, that went down a lot to only 35% when subjects were exposed to falling only. So they basically had a strong tendency to follow the role model. Now, we should, of course, look at, and we did look at, the individual behavior, right? Because these are all proportions of the total number of subjects. And again, and Iona did a lot of work on that and published it also. It's too much to report here. There are indeed individual differences, right? But it's a majority, but only a small majority of people who follow consistently the role model. And then there's almost one quarter of people who are inconsistent, and maybe 20% who don't pay attention and don't change their behavior. And then we became interested in how L2 speakers, learners of German, would behave in the same situation. So we tested them, and I'll cut this story short. And the gist is, yeah, French learners of L2 German converged to Mirabella 2. And indeed, both in the segmental and in the prosodic features. Here in the right panel, I just repeat a pattern that we just saw for Ich and Ich, for the native speakers. And in the left, we have the learners, the non-native speakers. And you can see that 80% of them had a preference for Ich at the beginning. So they basically followed the textbook, the instruction books, I guess. And they went down to 50% after being exposed to Ich. And for intonation, here they were quite unsure. So almost 50-50 used a falling or rising intonation contour for the WH questions. But in round one, when they were exposed to the falling one, then the number of people producing falling contours went from 44 to 63%. And then they basically fell back to their original pattern in the second round, when they heard only rising patterns. Now let me try to put this together a little bit. So here we have 20 individual subjects and their convergence behavior on 3 features, right? On F0, the intonation contour, on Ich, and on EE. So each ribbon or tier corresponds to one experimental subject. So there's 20 of these, right? And they're quite, so the majority of the people suggest, converges on 2 features. So there's not a single one that actually converges on all the features. And there are 2 guys who do nothing, basically, the gray ones. Right? They don't converge. In fact, in the task for E and A, there were 3 who had a substantial divergence from the role model. So they did the opposite of what the role model did. I can't go into that a lot, and we didn't really follow up on this, but an interesting behavior of a diverging accommodation or disaccommodation has also been made by the Stuttgart people, and we maybe can discuss that in the discussion time. So maybe keep in mind divergence. And the patterns it's difficult to compare quickly here, but overall the pattern is again relatively similar in natural versus synthetic conditions. So in summary, users in fact accommodate to speech output of simulated spoken dialogue systems. However, they show highly individual patterns in the behavior, in that the performance in terms of accommodation on one feature does not necessarily predict performance of accommodation in other features. On the group level, we see convergence overall for question intonation and for the consonantal contrast, and rather maintenance for the vocalic contrast. On the individual level, excuse the typo, we see convergence and maintenance, primarily convergence and a bit of maintenance for intonation. We see all three patterns, even divergence for the vocalic contrast, and we see primarily maintenance again for the vocalic contrast. So let me spend the last 5 minutes on interactions, on experiments where our subjects interacted with an automated assistant, a virtual assistant, in two conditions actually, in a solo condition. So there's one person interacting with Alexa. And then we have a confederate condition where there are two interlocutors, two human interlocutors, one of which was simultaneously also interacting with Alexa. The other was a confederate of the experimenters and was not allowed to interact with Alexa. So in this confederate condition, the two humans talk to each other, but occasionally they involved Alexa to retrieve some information also. Okay, we had two scenarios, two tasks: a calendar scenario, scheduling a meeting, and a quiz scenario with trivia questions. So we're interested in whether interlocutors would accommodate at all or to a different extent when interacting with humans and computers simultaneously. And we wanted to compare the effects and interactions with different types of addressees. In the calendar task, the blue distribution here corresponds to the participant, and this is on F0 on pitch, right? And so this is the distribution of pitch when this participant interacted with Alexa, which is the red distribution of pitch. Alexa has a female voice. Whereas you can see that when the blue guy was talking to the confederate, basically that was an overlapping distribution. So the participant changed their pitch patterns depending on whether they were talking to the confederate or to Alexa. For quiz, there's no such thing. I can cut this short. So we had lots of interactions. For 74% of all the interactions, we observed a significant difference in pitch, in F0, and even 89% in intensity, but there was nothing in articulation rate. So speaking rate, as tempo, was not accommodated for. So the degree of convergence and also the speed with which it happens during the course as the conversation unfolds varies a lot between the tasks, the experimental tasks, but also for individuals. And of course, if you want to build an adaptive dialogue system, then this kind of somewhat inconsistent pattern is of course difficult to, a big challenge to implement. So the idea for an adaptive spoken dialogue system would be to produce individualized speech output, right? Rather than, so what we now have is this, the same voice doing the same thing no matter who interacts with the system, right? And we would like to adapt and accommodate to the interlocutor. And Eran has implemented a component of a spoken dialogue system that performs this adaptation. So it detects and analyzes and tracks a small number so far of features in the input speech, right? And performs adaptation based on our experiments and imposes these on the output synthesis. This is the general idea. So, of course, we've used the contrast that we've studied before. This is a computational model, a complex one, right? And with all these models, you have a big problem. You have many parameters, you have many degrees of freedom, and there's always a danger of tweaking the system such that it behaves in the expected way too much, so like overtraining, basically. But there are a few interesting parameters to work with. One is sensitivity, so to detect the user's speech in specific contexts, speech patterns. Then the convergence rate, how quickly to converge, how far you want to go with convergence, right? Because you don't want to sound exactly like the interlocutor. That would be like mockery or mimicking. And Eran also tried to build in various exemplar theoretic assumptions about, pool size, update frequency, weighting of recency of tokens, etc. So there are lots of things to play with. And he used the tachotron framework, neural net-based synthesizer to implement that. Wrapping up, vocal accommodation, phonetic convergence are an established fact in human-human communication and have now also been observed in human-computer interaction in a range of conditions. It is assumed that a vocal accommodation may improve naturalness and efficiency in HCI, but in order to do that, it would require really an adaptive spoken dialogue system that can reliably detect features in the input speech and generate adapted output. And we need a lot more research in that area. Thanks a lot for your attention.